Greetings and welcome back to a new video about three-phase rectifiers. In this example we will discuss the controlled three-phase rectifiers using the 6 thyristor configuration as shown here. There will be an DCM operation, so discontinuous current mode, and we will have a resistive load in this example. This will be a design example where we see how we can design this circuit for a specific average load voltage. Of course we will see everything step by step in our calculations and verify these in MATLAB Simulink simulations. Okay, let's see what the objective is. It's stated here, we like to design for an average load voltage of 75 volts. For this circuit, you see again here the 3 phases and the 6 thyristor configuration, which has each of them has a gating signal G1 up to G6, and we have our pure resistive load here R. The sources are star connected, having the values of 400 voltage as the peak voltage, phase voltage, and the frequency is 60 Hz. And again, the phases are 120 degrees from each other. The load is, in this case, 50 ohms. What we like to know is what the delay angle for these thyristors must be in order to get this average load voltage of 75 volts. And in addition, we like to calculate the average load current, the RMS load voltage and the RMS load current, the absorbed load power, and finally the power factor for this design. Let's discuss the conduction modes briefly. If we have a delay angle alpha, which is smaller or equal to pi over 3 radians, which is then in this case 60 degrees, then you have always continuous current mode for all passive loads. So resistive, capacitive, inductor, doesn't matter if this is the case for your delay angle. But if this is not the case, for example, you have a larger, let's say 65 or 70 degrees, or in this case larger than pi over 3 radians, you have always this continuous current mode for a pure resistive load, but it might be DCM for other loads like the resistive inductive or resistive capacitive inductive loads. You don't know this, so it depends on the couple of things like the impedance angle. But you also have always DCM for all passive loads, again the resistive, capacitive, inductive, if your delaying is larger than a pi over 2 radians, which is then 90 degrees. So if this is the case, you have always DCM, but this is not necessarily the case for active loads having a back EMF battery or any battery powered devices. So if your load has also some kind of a battery which is charging, then you might not have a DCM even though the alpha is larger than 90 degrees. So this is in summary how the conduction modes are. So let's also look at the voltage expressions from these phase voltages. So we know the phase voltages are given, and the line-to-line voltages we also need to use for our calculations. So these are given in time domain. We convert that to omega t domain, which is let's say easy to work out later for our calculations. So we actually take here the 400, which is Vm, and we replace actually this 120 pi t by just omega t. And we convert this 120 degrees and this 120 degrees in radians, which is actually shown here. Okay, the line-to-line voltages are the differences between the node A and node B voltage. So node A and node B, which is VAB, that's shown here. And if you do the math, you get actually this result, which is the square root of 3 times the Vm. So the voltage between these two nodes as the amplitude is square root of 3 times larger than the 400 volts. Similarly for VBC and VCA, that's actually going in the similar fashion. How about the load voltage? Load voltage can be then expressed by actually looking at this load voltage. This is between these two nodes always. So that means, for example, taking this as an expression, you can say it's VLL, where that is the line-to-line voltage, which is the square root of 3 times the Vm. That amplitude is our VLL. Okay, and in this case it is now 693 volts if you calculate that using this 400 volts for the phase voltages. Okay, let's continue and we'll look at our design in this case. Now we like to know what our delay angle is, but the problem is we don't know in which conduction mode we are operating, so we need to check that. So what is the conduction mode? That is actually the problem in this form. It could be CCM, but it could be also DCM. Again, CCM for conduction mode, for the continuous current mode, and here or conduction mode or discontinuous conduction mode. If you have, and you know for sure that you have a DCM, then you can use this formula for your average load voltage, because that was our objective for design. So you can look at the VLL, you can look at what you need, in this case 75, and you can calculate your alpha. If that is not the case, it is DCM, then you need to use this formula, and you see here the similar expression but then a little bit different. Again, we can calculate here the alpha from this expression. For example, we assume it is CCM, and we go with these values. Again, the VLL is shown here, so we use this and we convert that to calculate the alpha. So you multiply the VO here by pi and then you divide by 3 VLL and take the inverse of cosine, so R cosine, and you have this expression. And we do the math here, you get here 1.457 radians, which is then in this case 83.59 degrees. Now let's see later what does mean. Let's also calculate that similar thing for the DCM, so calculate the alpha. So you see you do here now pi times this VO, and you divide again by 3 VLL, and then minus 1. And then you do inverse of the cosine of this complete part. And you also need to subtract this pi over 3 here. That's actually all shown here, one picture. And then you have your expression here, which substitute all the values. And you get here, alpha is 1.614 radians, which is in degrees, 92.45 degrees. Now, which one is now the correct one? So which one do we take? Do we take this one or do we take that one? That's actually the question in place here. Again, the review of our conduction modes we have just discussed. We know that the CCM for this condition, DCM for these conditions, and we have also DCM if you have a larger than 90 degrees for your alpha. But if I look at the values, the alpha here is 92.45 degrees, which is already larger than 90 degrees. And I have a pure resistive load here, so it is not necessarily a different load. So this is definitely the situation where I can use, and this is not possible because if I have a CCM and I have a pure resistive load, I cannot have a larger than 60 degrees because that will then contradict this statement here. So this is now the situation we need to use. That means the valid alpha we have for this example is 1.614 radians, because that will fulfill the conduction mode we have discussed here. So we will use the DCM operation and we will use an alpha of 1.614 radians for this situation. Okay, now moving on and going to the next steps. Let's first bring up the figures for this situation. We have here the phase voltages, which is here given in brown. The blue one is again 120 degrees shifted to the right, and the green one again. So you see actually the VA, VB and the VC we have seen before. This is the load voltage, this is given in red, and this is the load current, which is given in here in pink color. And these are the values given here in the horizontal axis in radians. So this is the phase. You see the delay angle, alpha minus pi over 2. It will then come to 0 at pi over 6. I mean, this is then alpha minus pi over 6, and it will come to 0 at pi over 2. And then it will get again back up at alpha plus pi over 6, and then repeat that process here. So you see here there is a period of pi over 3, and again the same thing, pi over 3, etc. also there. And you see here the thyristors are firing in such a way that the T6 is fired, and that means this one is then fired such that the output voltage is then coming up. But the firing for the T6, which this thyristor, is not happening at alpha, but alpha minus pi over 6. That's a special scheme to operate this in the three-phase controlled rectifier form. And the T1 is also fired, but not at alpha, but alpha plus pi over 6. So that's actually what you see here. And the T2 in a similar form, and T3 and T4, they are all fired. And you see also by firing, you actually bring up your output load voltage and also your load current up. And this process will then start over, and these are the line-to-line voltages, which you see here. So VCB, VAB, etc. So at some point, we then again repeat the process. So after this VCA, we come here, this part here, which is then again this VCB. So our load voltage expression will be then VAB, which is then this part where we take actually between the T1 and T2 firing, which is then between the alpha plus pi over 6 and alpha plus pi over 2. But our function is only valid or non-zero between the alpha plus pi over 6 up to 5 pi over 6, which is of course the non-zero condition, but the period is running from this point to that point. Again, the VLL here is given by this value. Okay, we know our expression now for our load voltage. What is our average load current? That is actually pretty straightforward. We actually could have done that already before, because this is 75 volts we need divided by the pure resistive part for our load, which in this case just resistor. That will result in 1.5 amps. How about RMS load voltage? Now, that can be done using the definition for the RMS. In this case, we know that we have a period of pi over 3, so we can do 1 over that period. And we integrate from the start here, so alpha plus pi over 6, and you need to stop at 5 pi over 6. That's actually what you see here, the lower and the upper limit. And you need to square your load voltage, and then take the square root of the complete thing here. But we know the VO, which is our load voltage, is expressed by this expression, so we can substitute that in here. And we also convert this 1 over pi over 3 by making the fractions by 3 over pi. That is of course more convenient. And you can also operate this square here and the square in the sign. That's actually all shown here. And then after some steps, you get actually this expression where you see here the expression for the VO RMS, which is our RMS load voltage. And again, you see here the alpha, which is our delay angle. We have determined already in order to get this 75 volts average load voltage. So we can substitute that in here. So 1.614, which was our radians, which is our VLL, which is here 693 volts, and that will result in 127.3 volts. Okay. How about now the next one, which is our RMS load current? Again, that is really straightforward as in question B using Ohm's law. So in this case, we use the RMS load voltage, you divide by the resistor, and you get here 2.546, almost 2.55 amps. RMS load current will be then used in question E for the absorbed load power, because there you need to have the formula, or you need to use a formula for the absorbed power where it's stated RMS load current squared times the resistor. That means we take this value, we square it, and times the 50 we have from our load, and that will result in 324.1 watts. Okay, the power factor, which is our final question here, question F, that is defined as the load power, so this is the true power, it's also called active power, divided by the apparent power S. And apparent power is given, in this case for the three-phase system, 3 times the RMS source voltage times the RMS source current. What is the RMS source voltage? Which is actually the VM, which is our phase voltage, divided by the square root of 2, because it's the pure sine wave, which will result in this 282.8 volts approximately. The source current, RMS, is also the RMS phase current. So this current here, IA, IB, and IC, are actually also the source current. So these are the phase currents, and that is related to the load current RMS by this expression where you see the square root of 2/3 times the RMS load current, and that will result in 2.079 amps. Okay, now when you use this and that value, you get here an apparent power of 1764 volt amperes, and if you take that here and use also the value from question E, you get a power factor of 0.1837, so almost 18.4%. Okay, let's bring everything here. So those are the values we just determined, and now we can continue. First, we look at our Simulink circuit and look at the data and also the values. This is again the 6 thyristor configuration. You see here the 3 phases, VA, VB, and VC. You see here also the measurements for the voltages for each phases, and that goes to also the scope here, so we will see that shortly. We also see here the load voltages measured and put here in the mean and the RMS values, so we will all see that one by one. First, we start with the average load voltage, which actually in this case is 75.02 volts, which is very close to what we needed, so this is indeed very nice. The average load current is 1.5 amps, so also as we have calculated. So this alpha will do the job for the average load voltage, and Consequently, our load current average is also correct. Our RMS load voltage here is 127.3 volts, which is also what we have calculated, so that's also correct. And then also the RMS load current, which is 2.547, which is very close to what we have here, so that's also very fine. The source current RMS is 2.079 amps, and it is here 2.08, so it is just a rounding off error. Again, this is also very close to what we have calculated, so this is all very nice. Okay, let's now look at the situation for the gating signal for our pulse generators, because these thyristors needs to get activated, and it can be done using the pulse generator settings, so we need to also discuss that in detail. So you see here the 6 pulse generators, so T1 up to T6 generators, and you also see here the scope actually for presenting them. I will first discuss how you need to set this in Simulink in order to get the values I get also in this design. So look at the T1 first. This is the parameters in the pulse generator for T1. You see here the amplitude is 5 volts. Your period must be 1/60 because this is the operating frequency. And your pulse width must be 1/3 of the complete width of your period, in this case 33.33%. That's actually what you should do. And your phase delay calculation should be done like so. That's actually shown here. So phase delay for T1 is then alpha, we have chosen in this case 1.614 radius, or in degrees 92.45. You substitute in here, you do plus 30, that is how it works, and then divide by 360 times the frequency of operation. And that will result in a specific delay time, which is given in seconds. And that's also shown here, so it is here 5.669 milliseconds. And that is actually how you need to do that. So in MATLAB, for the pulse generator, you need to convert your angle into seconds. And for the T1, is that for T2 in a similar form. You see here again the same amplitude, the frequency, etc., and the pulse width. The delay there must be, in additionally, also you need to add here plus 60, and similar process actually, and then you get here 8.4468 milliseconds, and that's all shown here. Okay, let's now go to the other two, which is the pulse for the T3 and T4. So those are actually in a similar form, so let me go one by one. So this is the T3, which is the blue one, which is for this. And that's actually shown here. So it is then 11.225 milliseconds. Again, you add another 60 for each situation. So this is the T3. And for T4, which is actually this red circle, that's given again an additional 60, and that will result in 14.002 milliseconds. It's also shown here. Okay. Now, final two, which is the T5 and T6 pulse generators. Those are actually also here. So this is the blue one, and that is the red one. And I also did the following here. I add another 60, of course, but also subtracted 360 degrees because that's the full circle to get actually to a point from the start, and you don't have any transients at the beginning. That's actually what I do. So you don't have to do it, of course, but it will be convenient for the plots. In a similar form, I also did that. So you see again here, I add plus 60 and then minus 360 degrees just to come early up. And that's all expressed here also. Okay, now look at the Simulink plots, because there you see more details, how that works. This is again the phase voltages. You see a brown VA, the blue one is VB, and our light green one is the VC phase voltage. This is our load voltage, the red one, and our pink color, or maybe the purple color, is our load current. To see some labels, let's go one by one. The blue one here, it has time of 2.891 milliseconds. Now, if you want to convert this time, which is given in seconds, into the radians, we need to multiply it by the operating frequency in radians per second, which is our 60 Hertz times 2 pi, that's this 120 pi. When you do that, you get here 1.090 radians. Now, if you look at where we started in the discussion before, that was alpha minus pi over 6, which is then also 1.0906, which is of course again reflecting to that time point here. This point here, where the conduction stops, so where the load current is reaching 0 again, which is then happening at 4.167 milliseconds, converting that in a similar form as we have done it here in radians. And that was happening at pi over 2 radians, which is then again close to each other. And actually, in this case, exactly each other. The final one, this green one, which is then happening at 5.668 milliseconds. Convert that again to the radians, similar form, you just multiply by 120 pi, and that will result here in 2.137 radians. And when you look at the discussion before we said here, it was alpha plus pi over 6, which is then done here. So this alpha plus pi over 6, which will result in 2.138 radians. Again, you see that really close to each other, so it's all very nice. All right, it was our example considering the controlled three-phase rectifier having a resistive load, and we have designed for a specific average load voltage. We also looked at what kind of a conduction we had before and used that value to come up with the specific delay angle, and that will be used for the calculations for this example. Don't forget to like and share these videos so that we can reach more people for these interesting topics. There are more videos about these topics and also other topics within the power electronics, analog electronics and control systems on this channel. So if you want to learn more about this, just look at the channel for more details. And if you have any questions about any other videos, just let me know. Stay tuned and see you next time in another video. Take care.